As a mathematics teacher, one of the things you constantly hear teaching a calculus course is, where are we going to use this in real life? Well, here's a situation where it does get applied to real life. And as we've said in classes, like, calculus is not an everyday type of use of mathematics. It's specialised, but it does get used in real life situations. So we, for example, a situation here, if you've got a manufacturer that wants to package 600 volume of 600 mils of milk in a rectangular prism. But what the idea of for that manufacturer is to minimize the packaging so they minimize the cost. So what would be the packaging he would use? So you just can't go start producing things and go, oh, okay, trial and error. We don't want to do that. Or manufacturers don't want to do that. So they'd get someone in to model that, and they would rely on using calculus to find the minimum value of packaging that they could use. So when you start talking about a minimum, wait on, we've been talking about maximum and minimum turning points on a function. Well, we could get a situation where we could model a graph of the packaging that could be used for the same amount of milk and look at, well, what's the amount of packaging that becomes a minimum. Oh, that would be what we would use. So that's what we're trying to do. The problems, what we're looking to do, we're going to solve here, pretty much go along the same lines of what we've done with the curve sketching. But we're going to get our derivative, set it equal to 0. What the main problem is going to be is determining what function to deal with. So, for example, here we've got a farmer is getting up a rectangular paddock and needs to use 1,444 meters of fencing, and the paddock will measure x by y meters. So we've got our paddock there, so our y's been cut off there. So they're all y's, they're x. And we want 6 rectangular paddocks. So each one's going to be x by y. So the problem we face, if we just look at our area there of this, would be 2x by 3y, which is 6xy, which is giving us a problem in that we have a function in terms of x and y. Doesn't work for calculus. We can only differentiate in respect to one variable. So what we need to do is to do the first part is get one pronumeral in terms of the other. Now it doesn't matter whether you get x in terms of y and y in terms of x. Depends. A lot of times the problem will describe that for you, tell you what you need to do. So get y in terms of x. So we know from here what our relationship exists about this fencing, because the 1,440 meters of fencing is all these lines here, which basically works out to the perimeter as well as these inside lines. So really we've got 2 lots of x there, 4, 6, 8 lots of x, and 3, 6, 9 lots of y would make up the 1,440 meters of fencing. So again, if we manipulate the 9y equals to the 1,440 minus 8x, and then divide by 9, there's y in terms of x. So that's just what we're looking at to get our one variable in terms of another. Then we said our area was 2x times 3y. So if we do our substitution of y there, we get an expression manipulating our algebra down in terms of x. So there's the expression we're trying to find. Our next step then would be to find the values of x and y, which the area would be greatest. Well, greatest, maximum. We need to find the maximum value of x. So 960 minus 32x on 3 would equal 0. So we get our first derivative, set it equal to 0, like we've normally done. Solve for a maximum or minimum turning point. 32x on 3 gives us 960. X would equal 90. And then we get that value of x, put it back in the expression we found in part 1 to get y. And also we need to test our first derivative. So test our second derivative. We can test in the first derivative. We've just got to prove maximum or minimum turning point. It depends on whether you want to use the first derivative or the second derivative test. But if we derive this one, we get minus 32 on 3, which is less than 0 for all values, so it must be a maximum. So there's how we prove something's a maximum or minimum stationary point, a maximum or minimum value for the problem. Pretty much doing it the same way we did to prove the the nature of a stationary point, because that's really what we're doing. The stationary points here provide either the maximum, in this case, or the minimum values that we could get. So it's solving for those values and then proving that. We must always prove it. That's either a maximum or minimum. A lot of times I see people do these problems. They get their values and go, oh yeah, that must be the maximum or minimum. Wait on. Even though there's only one value and it's only going to prove maximum or minimum, you still need to be able to show that it is the maximum or minimum value. Sometimes you might get a problem where you're going to get two values. One might be the maximum, one might be the minimum. Not always the case, but make sure we always test that in the second derivative or test the first derivative. So what steps are we looking at in doing these problems? One pronumeral in terms of the other. Always needs to be done because we've usually got one or two, or maybe three, but generally two pronumerals in the function, so we need to get that expression in terms of one variable so we can solve for a maximum minimum turning point, because you can't derive an expression when you've got two different variables in there. So just be wary of that. Solve that maximum minimum and show, and that's important. Show that's the maximum or minimum once you've found the actual values, because you need to prove that it is that, either do first derivative or second derivative.